So, good morning, everyone, and welcome to We Meet at Digital Days. My name is Marie-Therese Kohl, and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is board level shielding and handling common mode noise in new high-frequency technologies. Our speakers are Ashiro Shen and Antonio Alcaria. They will hold the presentation and will answer your questions. Before we start, I would like to point out one thing. You will be muted during the presentation. This means that you cannot ask questions via microphone during the presentation. Nevertheless, you have the opportunity to ask questions during the presentation at any time via the chat function. You will find the chat function in the webinar control panel. The presentation will be about 30 minutes long. The chat questions will be answered in a Q&A session following the webinar. There are 5 to 10 minutes in addition scheduled for this. If we are unable to answer all your questions within this time, we will answer them via email afterwards. If you still have any other questions left, just mail us at exhibitions@we-online.com. We will try to answer all questions promptly. At the end of the webinar, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our event. You will receive the link to the presentation in the next few days. Also, the recording will be available at our website shortly. But now I will hand over to our speakers, and I wish you an exciting presentation.
So good morning, everyone. Thank you, Marie-Therese and all the team for organizing these webinars. So we are today here to talk about board level shielding and how to handle common mode noise in new high frequency technologies. I'm Antonio Alcaria. I will start with this presentation. Later on, I will hand it over to my colleague Ashiro Chen. I hope everyone took their coffees and we can enjoy this presentation. So we did this small introduction. We are going to talk about differential signaling, what it means, then about coupling and radiated noise. This is related to the differential signaling and the problems we can have with this kind of technology or kind of designing. Then we will talk about how to solve these issues with the shielding cabinet and also the common mode choke. And finally, we are going to have some time for questions from your side. So first of all, why do we have differential signaling, or what is this? Normally, this is the very common design. We have two lines, positive and negative, and then we put these two lines together. And we have these two conductors side by side, with the same current flowing in opposite directions. So we have a loop. And in this loop, we have one current that is equal. So why do we use differential signaling instead of using one line or one conductor? This is because of the advantages we have using these signals. The first advantages that come to our minds when we think about these designs is that we need to use lower voltages. Why? Because they are able to maintain the signal to noise ratio, and they have a reduced power consumption. So these are the first advantages. We can use also higher data rates using this kind of designs, and also we are reducing, when using this design, we are reducing the EMI that can be caused by the design. Why? We have 2 points. The first one is that we reduce the crosstalk, because if we have one line, we're instead of 2 lines, we can have noisy tracks that can be affecting each other. If we have 2 lines, we have a more or less symmetrical position where the one signal, one line is canceling the other, and then reducing this EMI or transmission of noise that we could have. If we have any kind of electromagnetic interference or crosstalk, as we said, from the other parts of the device or the design, or for the traces, this noise that is coming from the outside affecting our design affects both the positive and the negative sides. So this noise is distributed, and then we have kind of a balance. So this helps also in reducing the effect of EMI affecting the design. That's why we normally use differential signaling. What's the problem that we could have with differential signaling? The most common is the common mode noise. Common mode noise is where we have the same noise coupled on both lines in our design. This could come for a difference in the impedance between these two lines. We could have also different grounding references between positive and negative, and also parasitic capacitance. All these different and small problems can cause a difference of impedance between these two lines. And then if we have some kind of coupling or things like this, then we could have different voltages coupled, or even the same voltage coupled on both lines. So we have the same current. Instead of having a loop and the current flowing in this way, we have the same noise coupled on both lines and flowing in the same direction. So we have the same current in this direction. In telecommunications, as I said, differential signaling is the most used design, but it could be due to the common mode noise. It could be a serious or potential threat because it is a source of RF interference in both sides. For interference coming from the outside and affecting our device, and also for our device and this design affecting being able to generate noise and radiating it to the outside. So now we're going to talk about some solutions that we have in order to solve this situation. So as I said, this design, this common mode noise can be radiated to the outside. And now we need to think that with the new technologies, like we have IoT, 5G, IO wireless link in the industry, and GPS signals, or GLONASS, Galileo in Europe, and so on. We have a lot of signals in very concentrated places that need to be working together. So the concentration of these signals joined to the common mode noise problem, for example, in lines, can generate that these external signals are affecting our device because they are coupling our device. Or as we have in the example on the bottom left, if we have two PCBs in our design that are close together, and we have one that is generating, in this case, we have an inductor, it's generating an electromagnetic field. This can be affecting another ICs and parts of our device. We cannot cancel this because this is a way of working of the inductor in this case. You can imagine here, instead of the IC, we have the line, a transmission line, or any kind of differential line on the top PCB. And then the noise will be coupled, and it will happen the same problem we were talking before about the common mode noise. This noise is coupled in both lines, and then we have current flowing in the same direction. And then our transmission line, our data line, is messed up. So how can we avoid these kind of things? One way of doing it is creating a Faraday cage effect. Here on the right side, we have the normal use for the housing, the behavior of the housing as a Faraday cage. So in this case, we have two examples. In the one on the left, we are using the Faraday cage to contain the noise that is generated by our design, so it is not affecting external devices. You know, by normative, we have to pass a lot of certificates about EMC and test, where in the lab it is tested if our what is the amount of radiation that our device is radiating to the environment. And the opposite, we have an antenna that is radiating our device and is trying to interfere with the proper working of our device. These are the two examples of using a Faraday cage in order to pass and to avoid these two problems. On the left, we are containing the noise inside, so we don't let the noise of generated to be affecting other devices. And on the right, we are using the Faraday cage to protect against external noises. This could be, for example, if very high speed signals like 5G are on the outside, that will be all around, or any case like this. So this can be applied also on a board level shielding. So it doesn't have to be only housing. We can apply it also directly on the PCB to shield special zones or areas that could be sensitive to external signals. So how do we use, what's the component we can use in order to solve these problems, to create like a small Faraday cage inside our design? The shielding cabinets. So the shielding cabinets are able to contain the noise inside itself. They act like a Faraday cage, a small Faraday cage. The last phase or conductive phase is the ground, so they are soldered to ground. So they are able to catch up this noise and redirect it to ground. As we can see here, we can see on the right side two pictures where we see that there's a noise source. In this case, will be any kind of high-speed signal generator or things like this. And by using this shielding cabinet, we are containing this noise inside and redirecting it to ground. So as you can see, if there is no Faraday cage, no shielding cabinet, then we'll have the issue of the picture on the right side. We will have a noise source that is affecting another parts. This could be, for example, that we have in our design, we have an RF stage, and close to it we have the power stages, or different design stages that are close together, because now also electronics are getting more concentrated and smaller housings. So we need to keep these stages separate, because if not, we'll have the problem of one of them affecting each other. For example, RF is a very sensitive design, and we need to keep always the impedance steady and the same. What's happening that we have some coupling that could be coming from common noise, for example. This coupling can be increasing the impedance of the lines in the RF stages. And then with the matching that we designed for our antenna is totally messed up. And the radiation pattern that we calculated for our antenna is not working anymore. So what do we do in this case? In this case, easily we can place a shielding cabinet over the RF stages, and then we are protecting all this sensitive area against these external noises that could be coming from the outside, or as I said, could be coming from another part of our device, such as the power stage. And this is the second part of the shielding cabinet, so it protects against external noise. As you can see here, we have containing noise, the ability of containing noise, and here we have the ability of protecting against external noise, sensitive areas, or a whole part of the PCB, and so on. So now we have this component that we released recently, is the shielding cabinet seamless. What's the difference here? What's the innovation here? Is that we have a shielding cabinet that is completely closed. It's especially designed for using it in high-speed signals and high-speed working frequencies. As we are going high in frequency, I don't want to get too much in the technical stuff for this short presentation, but as we are going high in frequency, the slots and the holes that could be critical for our device are becoming smaller. Why? Because as higher we are going in frequency, the less they need to escape or to be conductive in some, to be going radiated through some conductive part. So if we think of a monopole antenna, For low-speed signals, we need a big monopole antenna, and for low-speed signals, like low frequency, for high-speed signals, for high-speed signals, we need small antennas. For low-frequency signals, we need very big antennas. So we can think of this as that in any conductive part of our device, like a pin or a slot through the housing, can be radiating, can be acting as antennas and re-radiating the noise. So these cabinets are designed to have no seams, no holes. It's a completely fully seam enclosure. And then they increase the Faraday cage effect. The good point also about this cabinets is that they have over 100 sizes available as a standard. This is quite good because normally when we need, or a designer needs, some kind of customization, this customization requires tooling to create the specific cabinet and so on. So by having this big portfolio of different sizes, it's easier for you and for designers to find one that already fits for the existing design. So as I said, this is the seamless shielding cabinet. As you can see here in the corners, and also normally normal cabinets in the corners are joined together or soldered. In this case, it's fully closed. This is due to a deep drawing process. The standard material is depleted steel. This seamless design is not only better for high frequencies, also in lower frequencies, we are increasing the shielding effectiveness. By shielding effectiveness, I'm meaning the attenuation that we can, that the cabinet can achieve. So this normally is called shielding effectiveness. This is the two-piece shielding cabinet. It has a clip-on system. So we have, this is because if we need in the design to have an after soldering visual inspection of the components inside and so on, there is also a version of one piece that can be requested for all the sizes. And it is designed for pick and place with this small supporting part in the middle. So as I said, this design makes it fit, especially for high frequency, because the shielding effectiveness is increased in the whole frequency range. But as we are reducing the number of holes and apertures in the cabinet, we're increasing a lot the Faraday cage effect, so we can go higher in frequency with the same shielding effectiveness. As we see here, the standard shielding cabinets are very effective, like with high shielding effectiveness until 3-5 gigahertz. From there, the holes that are coming for the design of the shielding cabinet can be acting like a radiating antennas, and the high frequency signals can escape through there. The seamless shielding cabinet, we are solving this part. We have one more thing to mention, is that there is also as a standard a one-piece solution and a nickel silver material. Why nickel silver? Because we recommend this material for applications where a high corrosion resistance is necessary. So for humidity environments, humid environments, and stuff like this, we recommend to use nickel silver because it provides a better corrosion resistance. So now I'm going to hand over to my colleague Ashiro. He will give you another clue or another component in order to solve these issues with a common choke. Thank you very much for your attention, and later on we will answer your questions.
Thank you, Antonio. And as he said, we will continue. Now we will talk about a different solution that we have also for these new interfaces. And it's a well-known component. We all know it's the common mode choke or common mode filter. But in this case, instead of a ferrite-based common mode choke, we introduced recently an multi-layer common mode choke, which is based in the transmission lines principle, And we designed it especially for the higher speed interfaces to resonate at Wi-Fi and LTE frequencies, which is the 2.4 gigahertz, while we allowed the high-speed differential signals to pass through unharmed. These chokes are LTCC based with inner structure based on the LTCC, sorry, and with extremely high-speed differential signaling up to 10 gigabits per second, we can use it. And as I said, it's designed to resonate at 2.4 gigahertz, where we have more than 30 dBs attenuation. The LTCC technology, or low temperature co-fired ceramics, it's a well-established technology and has been used for many years. And in this case, we're using the transmission line principle and with different layers to design this choke. And the advantage of this choke is that it can work in the higher frequencies that are coming, and we don't have the losses that we have at this kind of frequencies, these high frequencies, with using a ferrite of nickel zinc, or nickel zinc in this case. So some advantages, as you can see here on the left, it's the small size that we can have with really low losses, high reliability, and it's really stable to temperature. So what is different with this choke or common mode filter? The switching speeds of the modern digital interfaces are getting higher and higher in speed. So with these high switching speeds, we are now able to achieve very high data rates and bandwidth. And with this, the noise problems come also at higher frequencies. These are some of the individual data lanes, switching speed of the state-of-the-art communication interfaces that we can find right now in the market. Also, USB 4 specification was recently released, and it will be coming for users in the upcoming months. Not so late, actually. Some companies are already working on it, so soon it will come. Here we can see the maximum speed the newer interfaces are working. As you can see, from USB 2.0 up to USB 4, the speed is increasing, and with this increased speed, as I said, we have different noise problems that we need to filter. And we realized that with the ferrite, it's really nice solution, but for really high speed interfaces, we needed a different solution. In this case, our common mode choke based on the LTCC technology. Here we have a small overview of the different USB standards and data rates as background information. As you can see, the standard is way more complicated than we originally thought. The data rate depends in the number of active lines or the standard. So in this case, generation 1 means 5 gigabits, generation 2 is 10 gigabits, and generation 3 corresponds to 20 gigabits. But the overall speed also depends on the number of active lines, as I said. So this is important to have in mind to filter our noise problems. So one topic to have in mind, it's the antenna descent. The descent is the degradation in sensitivity due to noise sources. So generally speaking, the noise floor should be much below the level of the useful signal. If the noise level increases due to poor SNR, signal noise ratio, it can make it very difficult for the antenna, the receiver, to pick up the useful signal. This phenomenon is called antenna descent, as I said, and is one of the main reasons why the communication failures occurs at 2.4 gigahertz due to the noise. So here we can see an example of the noise, a USB 3 transmitting from a notebook and producing some noise from some different cables or affecting the Wi-Fi antenna. In the end, what could happen is that we will lose this communication because they are resonating at 2.4 gigahertz. For that, it's what we need this new choke that we developed that can filter this 2.4 noise. Here it's an example of 2.4 gigahertz noise generated by the USB 3.1 generation 1. The source for this data, it's Intel's white paper titled USB 3 Impact on 2.4 gigahertz Wireless Devices. The USB 3 specification requires the data to be scrambled and uses a spread spectrum technique on the clock, which can be modeled as a sinc function. The sinc or sampling function in the frequency domain representation for the spectrum analysis, which is obtained by the Fourier transform of the rectangular signal. Important thing to note here is that the data spectrum is very broadband, ranging from DC to 5 gigahertz. The side lobes that you can see can be totally ignored. In fact, the design is based on ensuring that the side lobes are neglected. Here we can see the data spectrum of the USB 3 transmit. And as you can see here on the left side, where we have a white paper from Intel, we have the different power levels. You can also see it on the right side. So at minus 90, it's totally unusable, and up to minus 30, where it would be the ideal. Here is a real example of the CCMF. 3 different cases of the channel loss are shown, as you can see in the different colors. So higher the channel losses, lower the Wi-Fi performance. But thanks to the CCMF, our multi-layer common mode choke, we have been able to filter the common mode noise and antenna descents to get the acceptable Wi-Fi performance. The yellow line, it's the limit for acceptable Wi-Fi performance, and as you can see here, the recovery from this choke is much higher. Here we can see the S parameters of the CCMF, and as you can see here, we have really high attenuation at the resonance point, which is the 2.4 gigahertz or 2.45 actually gigahertz, where the Wi-Fi and LTE technologies are working. As you can see, this common mode choke was designed to focus on this resonance. Comparing to the traditional, we can say common mode chokes, which are ferrite based, we have a wide broadband where we have attenuation around at different frequencies. But in this case, for these new interfaces with higher speed, higher switching, we designed it to resonate at this frequency. So thank you, everyone. That was the presentation for today. And now it's the moment for the questions, and we will be pleased to answer any of your questions. Thank you.
Yes, thank you, Antonio. Thank you, Ashiro, for your interesting presentation. As Ashiro mentioned, now we would like to turn our attention to your questions and wait a little second until some questions have come in. And you can enter your questions in the chat function in the webinar control panel. There's one first question, Antonio and Ashiro. Why would you recommend ceramic-based choke?
Well, we recommend this ceramic-based choke and also the ferrite-based chokes, but especially in this case for the interfaces we are talking about, this one, because at higher and higher frequencies, we are talking about 10 gigahertz, 9, 12 gigahertz, even higher. this magnetic or ferrite core has have some limitations, and with these limitations, we can see that the cutoff frequency it's lower than the frequency we are interested, or where we want to filter this noise, and we have big losses in this frequency with the ferrite bait, and the attenuation, the level of the attenuation that we need for Wi-Fi or LTE has to be higher. That means we need in the order of 20, 30 dBs, and this attenuation we can achieve it with this new LTCC based ceramic material that we developed for this choke.
Okay, thanks, Ashiro. And one attendee wants to know why you use 2 ground pins.
Okay. Yes, I suppose he took a look in the website. You can see that a part of the 4 pads that we normally have in a common mode choke, in this case, we also have 2 more pads. So in total, we have 6, and 2 pads are ground. Actually, they were designed to be ground pins, and this is because as it is based on the transmission line theory, and it works as a low-pass filter for differential mode and notch or band stop filter for common mode. The ground pins are necessary for this common mode suppression circuitry. So it's because of the design itself of the choke that we need to connect also the 2 grounds to make the choke work as a common mode filter.
Okay, perfect. Thanks. And one more question. Can the shielding be used to remove heat from IC?
I think this one is for me. Yes, it can be used also as the housing. It can be used also to dissipate heat. The thing is that you need one important part to take in account when doing this is that when you use the shielding cabinet, and then you have some IC or microprocessor or some processing unit that gets hot really high, so really hot. What we need to do is to fill the space between the top of this part that is getting really hot and the shielding cabinet. Normally what is used is some kind of conductive gap filler, the thermal gap filler, like when you can also find on our web page, or you can use it is used also some kind of potting that could be thermal conductive and things like this. But yes, it is used in this way because this is a metallic part, so it can help like a heat sink.
Okay, thank you. Another question is, why does lower voltage in differential lines results in low EMI?
So in this case, with the lower voltage in differential lines, yeah, we have a low EMI because the lower voltage means it's an easier transition in states 0 to 1 and 1 to 0, and therefore, thanks to this, easier transition, we can see that we produce the less EMI problems.
Yeah,
That's
something to add is that as we have these small voltages, because we don't need high voltages, as Asiro was saying, that we need 0 to 1, for example, to mark these 2 binary levels. The thing is that as we have these 2 lines, we don't need to have this much high power in order to drive whatever is inside the circuit with this differential mode. That's why, besides the low voltage, we're reducing the EMI because we are dividing whatever it could come in terms of noise between 2 lines instead of only 1. If we have only one, you need to think that you only have one victim for the noise. If we have two, and this noise is divided, and as these lines are symmetrical, then between positive and negative, if we have the same difference, then we are kind of way we're canceling this noise, part of it. This also depends on the design and this case of a study and of some research. But yes, we are canceling part of this noise, so that's why it helps to reduce the AMI.
Thank you, Antonio.
Okay, perfect. Thanks, Antonio. Thanks, Ashir, for answering the questions. If there are any questions left, we will answer them via email afterwards. But for now, I think we are finished with this presentation. Thank you very much for your attention, and I hope you enjoyed our presentation.
Thank you. Thank you.
Goodbye.